Hi class, in this part of Chapter 14 we're going to talk about the actual nuclear fusion process that goes on inside the sun, and then how do we know that that's what's happening, what's some of the evidence for that. So the idea is that in the sun you've got particles that come together, mainly protons. There's protons and electrons flying around inside the nucleus as well as other things, and then the protons come together and they stick. But normally they repel each other because they're both positively charged. Each proton is positively charged. They don't want to be near each other. But if they get close enough, there's another force in the universe called the strong nuclear force that'll actually hold them together. So they'll stick together and form, a bigger nucleus. So nuclear fusion is this process of the particles coming together to form a bigger nucleus. In this case, we see two protons coming together and forming a proton and a neutron. So this is the process we'll be talking about, where a proton actually turns into a neutron, but some other things come out in that process. And the other nuclear fission process that happens inside nuclear reactors we use to power for electricity. It's sort of the opposite process. We're taking a large nucleus and it's breaking into two smaller nuclei. In that process, you also get energy out as well. So both of these processes give you energy in various forms, but there is a limit to each of these processes. You can only get so big in terms of making nuclei before it actually requires energy to do it. And you can only break nuclei apart to get energy out up until you get to some smallest sort of nucleus that to break it apart, you have to actually use energy. So you don't get energy out all the time. So what we need to have this happen is we need very high temperatures so that the particles are moving very fast. And we need there to be a lot of them. We need high density. We need high pressure and density so that the particles are likely to get near each other and have a collision. If you have high speeds but you don't have a lot of particles, they might just go flying past each other and not even have a chance to collide. So there has to be a lot of particles, high density and pressure, as well as high speed to overcome the repulsive forces. So these two protons don't want to be near each other. So if they come close to each other, they'll most likely kind of diverge away from each other. But if they come toward each other at high enough speed, they could get close enough so that strong nuclear force can take over. So they have to get close enough for that force to actually take over and hold them together. So the process we're going to look at is called the proton-proton chain. And the net result of it is that you take 4 protons, ultimately, and convert it into one helium nucleus. So 2 protons have been turned into neutrons. And in that process, you get that nucleus, the helium nucleus, as well as energy. And that energy takes different forms. So we'll look at what the energy forms are and the different steps in this process. The first step is in the nucleus. Again, you have all kinds of protons flying around. You also have electrons and some other particles as well. But the first step is to take 2 protons and actually have them collide and stick together. When they do that, you'll get a proton and a neutron. But you'll also get out this little red guy, which is labeled over here as a positron. That's an anti-electron. That's an electron with a positive charge instead of negative. And then you have a neutrino that comes out as well. And a neutrino is a really, really light particle, almost zero mass. Travels at almost the speed of light. And once it's created, it kind of just flies right out of the sun without interacting hardly with anything. And so on Earth, we actually can detect these neutrinos. And we'll talk about this a little bit later, but we detect these neutrinos, and by measuring kind of where they're coming from, we see that there are a lot of neutrinos coming from the sun. And that gives good evidence that this process is in fact going on inside the sun, this nuclear fission process. So this first step in the reaction is to take 2 protons together to form what's called a deuterium nucleus. It's a proton and a neutron stuck together. And this happens all over the place. This is happening all the time inside the sun. But to get to the next step, you take one of those deuterium that you created, and it has to collide with another proton. So another proton comes along and has to collide with this deuterium, and what happens is that you don't get a proton converting into another neutron, but rather you get this proton sticking to the deuterium nucleus. In that process, energy comes out in the form of gamma rays, so pure energy, light. So far, what we've done is we've taken 2 protons and a third proton, and we formed this is called a helium-3 nucleus. So it's not quite the end result yet, but it's a helium-3 nucleus. And also we've gotten out a gamma ray, a positron, and a neutrino. To get the final step, we actually have to take one of these helium-3 and combine it with another helium-3. So these first two steps, step 1 and step 2, have to actually happen twice so that we can get 2 helium-3s. And then those 2 helium-3s come together, they stick to form a helium-4, and 2 protons pop out from there. So the overall result is that we have 4 protons going in, we have 2 gamma rays coming out from step 2, we have 2 neutrinos coming out from step 1, 2 positrons coming out from step 1, and we have 1 helium-4 nucleus coming out, and that's the end result of this particular fusion reaction. The proton-proton chain is what it's called. So 4 protons going in and all these other things coming out. If you were to measure the mass, initially you've got 4 protons, measure their masses, individual masses, 4 protons, add them together, you get a certain amount of mass. If you measure the mass of this nucleus and the mass of the neutrinos and the positron, they have mass, add all those masses together, the total mass that you started with is more than the mass that you end with. You actually lose mass in this process. And that is where the energy comes from. Energy comes from mass. So Einstein's theory of relativity gave us this equation basically that shows us how to calculate how much energy we get from a certain amount of mass. That's E equals mc squared. So if the mass goes down in these reactions, you're getting energy out in some form. And in this case, it's the form of gamma rays, and also in the form of the energy of the neutrino and the positron. Eventually, this positron will collide with an electron and will be annihilated, and the electron and the positron will disappear, and you'll have light formed. So pure light will be forming in that collision. Gamma rays are already pure light, and these neutrinos are just going to go flying out of the sun. They don't do very much in the sun itself, but we can detect them. So what would happen inside the sun if a slight rise in core temperature led to a rapid rise in fusion energy? So suppose we had a slight rise in the temperature of the core. That would cause, and it does cause, an increase in the rate of fusion. Higher temperature means things are moving around faster. They would collide more vigorously. They would collide more frequently. We'd get more reactions happening. We'd get more energy produced. So would the core expand and then heat up slightly? Or would the core expand and cool? Or would the sun blow up like a hydrogen bomb? Well, luckily, C doesn't happen. The sun doesn't explode like a bomb. But does it expand and cool or expand and heat? Remember that the expansion is being, it will expand, and so the expansion is being caused by the increased reactions, increased rate of reaction. But what happens to a gas when it expands is it then cools, right? So when gases expand, they cool. So it's the increased fusion reaction that causes the expansion, but the result of the expansion is that the gas actually cools. And so the temperature is going to then go back down. The temperature will go down, and it'll keep that fusion rate from increasing out of control. So this is something we call the solar thermostat. It keeps the fusion rate at a fairly steady rate over time. Gradually, as time goes on, the fusion rate may be changing because of the mass of the core changing. Fewer and fewer particles might be available and things like that. So there are changes in the long run, but from one day to the next, the fusion rate stays pretty constant. So the solar thermostat, again, is this is kind of shown by this model here. A slight rise in core temperature gives rise to more reactions. More reactions heats up the core. It makes it expand. It increases the radiation pressure pushing outward, and that makes the core expand. But that expansion actually causes a cooling down of the core. And that cooling down then causes the fusion reactions to return to a normal rate. In the other direction, if the core dropped in temperature, the fusion reactions would decrease, and that would lower the pressure outward. Gravity would win a little bit and squeeze the core. That squeezing from gravity would increase the temperature of the core, and that would then speed up the reactions to bring them back to a normal rate. So there might be fluctuations in the fusion rate, but on average it stays pretty steady. These slight fluctuations may make the core get a little bit bigger, a little bit smaller, and so on, but on average the fusion rate stays pretty constant over time. So how does the energy get from the core to outside the sun? So we talked about the different layers of the sun, and light, the energy from light has to come out of the core ultimately and go through the radiation zone. It then has to go through the convection zone and then out into the photosphere, and then eventually turns into visible light. So the energy that comes out through the radiation zone, we had said, is basically in the form of light. And the light is not getting absorbed by atoms, because atoms, it's so hot in the radiation zone that atoms have a hard time forming. And so the light is just kind of like bouncing off of things. It's like bouncing off of electrons and protons as it tries to escape. So it forms this zigzag pattern as it tries to leave the core. And it takes a very long time for the light to actually make its way to the edge of the radiation zone, and ultimately for all that energy to leave the sun. Once that energy gets to the top of the radiation zone, then to the bottom of the convection zone, it's cool enough down at the bottom of the convection zone so the gases can absorb the energy now. When the gases absorb that energy, they get hotter and they rise up. And as they rise up, they get to the top and they lose their energy. So there's kind of a hotter spot here on the surface of the sun. They lose their energy and then they kind of fall back down and they cool off and fall back down. The cooler gases sink, the hotter gases rise. So this is convection, this constant boiling, this constant bubbling of gases up and down and up and down. So on the surface of the sun, it looks very blotchy. You see these hot spots and cool places in between. Here's a picture of the sun, these very hot spots in here, and the cooler areas around them. So the hot spots are where gases are rising, and the cool spots are where gases are falling. So how do we know this is going on? There's a couple of things we can do. We can look at the sun in different ways. We can make mathematical models. We can look at the sun in terms of the neutrinos that it gives off, and I mentioned that before. We can also look at the sun in terms of how it's vibrating, how is it sort of pulsating in different places. It's a big ball of gas, and like if you took a water balloon and filled it with water and you kind of tapped on it, you would see it kind of, the water kind of fluctuating. You'd see vibrations in the water. In a similar way, this is a ball of gas, and if something's going on inside that's maybe causing, say, the core is kind of getting bigger and smaller or something, that contraction and expansion is going to sort of propagate outward through the star, and you'll see sort of oscillations at the surface of the star. So we can measure these patterns of oscillations with the Doppler effect. If we look at a certain region of the sun and we look at the light shining from it, if that light is moving toward us, if that surface that's emitting the light is moving toward us at one moment, that light is going to be slightly blue shifted. If later that portion is moving away from us, that light is going to be slightly red shifted. And so we can look at the Doppler effect of the light in different parts of the sun over time and see how the surface of the sun itself is sort of bobbing up and down or oscillating or fluctuating. And that gives us some information about what's happening inside the sun. It's very similar to how we use earthquake waves, different types of earthquake waves, and measure how they travel through the earth to determine the structure of the earth, even though we don't drill down far enough to actually see it. We've never been to the molten core of the earth, but we know it's there because of the way that earthquake waves travel through the earth. And other layers as well we know exist because of studying the motion of earthquake waves. So in the same way, we can study sort of like sunquake waves, if you will. So if we look at data on these vibrations, these solar vibrations, and compare them with our mathematical model of what's inside the sun, they agree very well. So in terms of temperature, this graph shows temperature as a function of fraction of the radius. So this would be out at the surface right here of the sun. This would be deep inside the core. And so the temperature we predict the prediction is the dotted line, and the data from the oscillation data, the observations, is this sort of orange line, and they match very well. So the observations from looking at vibrations and then the model, the mathematical model, match up very well. So we're pretty confident we know what's going on inside the sun. And then the neutrinos that were created in this reaction, they are observed in what are called neutrino observatories that are actually dug way down deep underground. So there are these big tanks of water of various kinds, and there's all these little bulbs, almost like large light bulbs, that act as detectors. And these are people in here that would normally not be in here when it's in operation, but it might be, they might be inspecting it right now. They're not going to get hurt by being in there. But the particular water that's in there might not be good for them. But they're mainly wearing these suits to keep contaminants from them getting into the detector. So they want very pure liquid in this detector. And when a neutrino goes in there, it could interact with one of the atoms or molecules of that material, of that liquid, and it could give off a little light, a little pulse of light. And from that, you can figure out where that neutrino came from and how much energy that neutrino had, what type of neutrino it was. So by looking at these neutrino observations, we can tell that there are a lot of neutrinos coming from the sun, and the number that we measure coming from the sun every second agrees very well with our understanding of the fusion reactions that are happening inside the sun every second. So what have we talked about? We talked about the high temperature of the core and the high density of the core, enabling protons to stick together, enabling the strong nuclear force to take over, to let them stick together, so we get some energy out. Gravitational equilibrium acts as kind of a thermostat, keeping the core temperature relatively constant. If it tries to heat up, the reaction rates will increase, causing the core to expand, but that expanding core actually will cool then, and then it'll get smaller, and we'll get the reaction rates to slow down. And then where does the energy come from? The energy ultimately kind of bounces out in a sense. The light kind of bounces out away from the core through the radiation zone. And then when it gets to the convection zone, it kind of bubbles up in the gases. It's sort of like a pot of boiling water. And then we can measure all these things. We understand that these things are happening by looking at mathematical models and comparing them with our observations of solar neutrinos as well as oscillations, solar oscillations. This is the proton-proton chain. We can just play this. We play step one. We have two protons here. They come together, and out comes a positron and a neutrino. So that's an E plus, and it's a little red dot, and that neutrino. Watch what happens when we play the next step. Here comes another proton. It's going to collide with this deuterium. But then watch what happens to this positron. It's going to collide with an electron that just happens to be coming by. And when they collide, they're going to form a pure energy, a light, a gamma ray photon. So let's watch those. There goes the electron, there are two gamma ray photons, and that neutrino is zipped off wherever it's going to go, and now these guys are going to collide and play our next step. So there's our helium-3, and there goes a photon, a gamma ray photon, and now there's helium-3 floating around, and it's just going to float around and move around pretty fast until it encounters another helium-3. And so it just happens to encounter another helium-3, and they stick together and two protons pop off, and now we have our final result, the helium-4. So you can play this over and over again. Again, this is available on your D2L, on the D2L site in Chapter 14. So the next section we'll talk a little bit more about this, and that'll wrap up the chapter. We'll talk about other features that we see on the sun, the prominences and solar flares and stuff, and how they interact with the Earth.